Physical properties of ethers. Ethers are in general polar molecules because we can see that the carbon-oxygen bond right here is polar, right? With a partial positive charge on carbon and a negative charge on oxygen. And therefore, ethers do have dipole moment. But when you compare the polarity of ethers with respect to alcohols, they are less polar. Okay, because there is only weak dipole-dipole interactions between them, because of which they are going to have lower boiling points when compared to that of alcohols. Can ethers participate in hydrogen bonding? In order to answer this question, let's take a look into the structure of alcohol and ether. For sure, alcohols will form hydrogen bonding because you can see that there is an hydrogen that is connected to an electronegative atom, right? But in the case of ether, there is no hydrogen attached to the electronegative oxygen. And therefore, ether cannot act as hydrogen bond donors, which means there is no intermolecular hydrogen bonding between ether molecules. On the other hand, ether has an oxygen which has the ability to bond with hydrogen in water or in alcohol, right? Therefore, they can act as hydrogen bond acceptors. Okay, so depending upon the number of hydrogen bonds that is formed, the solubility of the ether is going to increase or decrease in water. Now let's see whether we are able to answer this question. Arrange these compounds in order of increasing solubility in water. Water is a polar compound, so anything which is going to be polar or anything which has pretty much the same polarity as that of water is going to be soluble in water, right? Or miscible in water. Okay, we know that hexane is a non-polar compound because you can see that there is no electronegative atoms on it. So this is as such is going to be non-polar. Okay, coming to the next compound, diethyl ether. Diethyl ether is a polar compound, but you can see that there is only one oxygen on it compared to two oxygens in ethylene glycol. And therefore, this should be the most polar compound, and therefore it should be the one that's going to be more soluble in water. Okay, so the right order of increasing solubility of these compounds in water is hexane is least soluble. Okay, and then comes diethyl ether, and then finally our ethylene glycol. This is the answer for this question. Reactivity of ethers. Ethers in general are resistant to chemical reactions, and they resemble hydrocarbons in their resistance to chemical reaction. And they also do not react with oxidizing agents such as K2Cr2O7 or KMnO4, which is potassium dichromate and potassium permanganate. And they are stable towards very strong bases. Okay, but one exception here would be tertiary alkyl ether. That would be an exception. Ethers are not affected by most weak acids at moderate temperature. And also, one important thing to say about ethers is they are excellent solvents because of their general inertness to chemical reactions and also good solubilizing properties. And here are some of the ethers which are used in synthesis as solvents. Alcohols and ethers have got pretty much similar leaving groups, and therefore both of them need to get activated before they can participate in any reaction, right? So the alcohol, when it gets activated, it's going to get converted into a good leaving group, water. And similarly, in the case of ether, it's going to get converted into an alcohol. So depending upon the substrate, the ether can undergo either SN1 reaction or SN2 reaction. Here is a representation of the ether undergoing substitution reaction. So in the first case, the ether will get activated, thereby getting converted into a good leaving group. So this is our leaving group, right? And when it is heated, it's going to form a corresponding alkyl halide. Now let's do this with an example. Here we have a tertiary butyl methyl ether. Now let's see whether it's going to undergo SN1 reaction or SN2 reaction to form the corresponding alkyl halide. In the first case, this oxygen with its lone pair of electrons is going to go abstract this hydrogen and the iodine is going to leave. This step is called as the activation. Okay, so this is going to go abstract this hydrogen and the I is going to leave. Once the ether is activated, and it does have a good leaving group, the leaving group can just leave from the molecule, thereby creating a stable carbocation. So here in this case, as the leaving group leaves, it's going to form the stable carbocation. In this case here, it is a tertiary carbocation, right, which is more stable. And in the next step, the I minus can act as a nucleophile, making a or attacking the carbocation, thereby forming the product. So this is basically an SN1 reaction, right? So in an SN1, all of this is going to be SN1 reaction, right? Where in the first step, the carbocation is formed, and in the second step, the nucleophile makes an attack on the carbocation to form a product. Now, if a relatively stable carbocation is not able to be formed by the ether, then it's going to go through the SN2 reaction. For the SN2 reaction again, the ether still needs to get activated, right? The first step is going to be activation of ether, wherein this oxygen with its lone pair of electrons is going to go abstract this hydrogen, and it's going to get converted into a good leaving group. Right? And in the next step, the I minus is going to make an SN2 reaction. It's going to do an SN2 reaction where this goes and attacks the electrophilic carbon, and this whole thing is going to leave. So this is our leaving group. This whole thing is going to leave, thereby forming a propyl iodide. Ethers undergo SN1 reactions unless they would have to form a primary carbocation. Alcohols can be activated in numerous ways. Say, for example, you can react it with PBr3, PCl3, or even sulfonyl chlorides for alcohols to get activated. But when you take the case of ether, ether can only be activated by protic acids, okay, whereas it cannot be activated by sulfonyl chloride. So here is the reason why ethers cannot be activated by sulfonyl chlorides. In the case of alcohols, let's see what is the mechanism here. So the first case, this oxygen is going to make a nucleophilic attack on this electrophilic sulfur, thrust these electrons onto oxygen. Those electrons are going to come back in here. And since there is a leaving group, that is going to leave, right? So now this is going to form an intermediate, which is going to look like this. Right? In the next step, pyridine is going to act as a scavenger. Draw the structure for pyridine. So pyridine is going to act as a scavenger, abstracting this hydrogen, and those electrons are going to go back to oxygen, right? Now you have an activated alcohol. This is one way to activate an alcohol, right? But when you want to employ exactly the same method for ether, there is not an hydrogen present in ether, and pyridine hasn't got any job for it. So say, for example, the intermediate that will be formed in this case is going to look something like this. And because there is no hydrogen to abstract, this reaction is not going to go proceed in the forward direction. Instead, it is going to go revert back to the starting materials. So on the whole, ethers cannot be activated by other methods than reacting with HBr or protic acids. Two hazards must be avoided when working with diethyl ether and other low molecular weight ethers. First, the commonly used ethers have low boiling points and are highly flammable. This is a very, very dangerous combination, and therefore ethers are always used inside the fume hood. Secondly, anhydrous ethers react with molecular oxygen at CH bond to form hydroperoxide. Here is the structure for hydroperoxide, where you can see that the oxygen has got added between the carbon and hydrogen bond. Hydroperoxides are dangerous because they are explosive, and this reaction proceeds through radical chain mechanism. Rates of hydroperoxide formation increases dramatically if the CH bond that is attached to the oxygen is secondary, like in the case of diisopropyl ether, because it can favor the formation of a relatively stable tertiary radical. Okay, so here in this case again, this is the hydroperoxide that is formed. Here is the hydroperoxide that is formed.